on the lab webpage, the course webpage, you'll see I will upload a PowerPoint version of the material that I present, so that, occasionally I make mistakes on the equations or something. If you want a more elaborate outline of the material that I'm presenting, you'll see the lecture notes on the webpage as well. So if you look at the lecture, if you look at the webpage, you'll see it for both Thursday's lecture and today's lecture. All right, so today what I want to talk to you guys about is the concept of minimizing a error function, something that we're going to try to optimize as we learn. And this is going to be a way to look at certain things like patterns of prediction error. So when you fit a function, if you go and look at the errors that you make in fitting, you should analyze those errors, because they'll tell you something about how well not only you fitted, but also what else you could have done to fit things better. And I'll give you some hints about this process of fitting. This will also be useful because down the road we'll look at problems associated people learning. So when people learn things, we can ask, what is the function they're optimizing? So we're going to optimize a loss function. It's going to be mean squared error. And we're going to see how to do that. And then later on, we'll ask, well, people learn to do things. What is it that they're minimizing? And we'll be able to compare that to so-called loss function. So this is mean squared loss function that we're going to be looking at. We'll look at a number of algorithms today. LMS is one of the algorithms we'll look at. It's a trial-by-trial learning where you make a prediction, you make an observation, you learn from the error, and then you update your, basically your model, then you try it again. We'll look at batch learning, where all of the data is available to you from the beginning, so you don't do trial-by-trial learning, you learn from the entire data set. We'll look at some properties of convergence of algorithms, particularly for batch learning, compare it to LMS, and you'll learn something about convergence of series, power series in particular. So a little bit of math associated with how series converge. Okay, so we have some data consisting of things that look like this. All right. And we're going to start with the regression problem, where x is some feature vector. So x is going to be some vector, maybe x1, x2, so forth. And y is going to be a scalar. And so we're going to ask, how do we learn to map a vector of features into an output that's a scalar? So this is the basic problem in regression. And what we typically minimize don't know how to spell, sorry. What we typically want to minimize is the average between the squared prediction error, where this is your prediction and this is your data. So we want to find some parameters, which we're going to call W, which are the parameters of our model that are going to minimize a mean squared error. So this is our loss function. The loss associated with observation y and prediction y hat is going to be the squared error. So the difference between prediction and observation squared is what we're going to call error. And so our objective is to minimize the expected value of the loss function, which is sorry. So the expected value of the loss is 1 over n, the sum of the loss of so we want to find the parameter w that minimizes the expected value of our loss function. I want to begin with the simplest of all problems, when we just have a line to fit to a scalar variable x and a scalar variable y. And I want to show you what we should expect in the patterns of error, prediction error, that we fit. So by understanding the errors that result from our fit, we'll be able to make sense of, did we do a good fit? We'll see things like, what should we do if we want to improve the complexity of our model, have some nonlinear elements, things like that. And so let's begin with the simplest of all problems. So our problem goes like this. Suppose that my model is this. And I want to find W0 and W1 that minimize the loss. And so what is the loss? It is the expected value of the difference between what I observed and my model. This. So it's a quadratic function of my parameters, and I want to find the parameters W0 and W1 that minimize this loss. And so this is my cost, if you will. And so let me call this loss the thing that I want to minimize, the derivative of the loss with respect to this, the first parameter that I'm interested in. Let's say W0 is my first parameter. Well, I want to find the derivative of this function with respect to my first parameter W0. That's going to be equal to 1 over n, the sum of yi minus W0 minus W1 of x. 2 comes to the front, so this becomes a 2. Derivative of the inside of this with respect to W0 is minus 1. Let's see if you can figure it. Take a look at that, see if that makes sense to you. Do you have a question about what I did? So what I did is that I said, here's a quantity squared that's summed. What I'm going to do is to find the derivative of it with respect to an element that's inside this squared bracket. So I'm going to find the derivative with respect to the whole thing, which is just this thing squared, so that becomes 2 times this thing, times the derivative of what's inside with respect to W0, which is just minus 1. So we set that equal to 0, and now what I want to show you, what does this mean? What does this equation tell us? What I have here is the difference between what I observed and what I predicted, right? That's my error. I'll call that y tilde. Error, my prediction error. And what this is saying is that minus 2 over n of the sum of my prediction error should be equal to 0. So what that means is that the sum of the prediction errors must be equal to 0. If I found the optimum W0, then my errors should have no mean. Mean should be 0. So if you plot y as a function of x, the errors, y tilde, as a function of x, you should see something. After you fitted your data, if you look at your errors as a function of x, it should be mean 0. All right, so that's our first bit of information. The sum of my errors should be 0. All right, now let's find the derivative with respect to W1. So what I have is that 1 over n times the sum of the inside times the derivative of the inside with respect to w. So this becomes a 2 becomes a 2, and the derivative of the inside with respect to x becomes, with respect to w1, becomes minus x of I. X of I is what's inside of this. I apologize for not putting it in there. So again, this is my, what I observed minus what I predicted. And so what this equation tells me is that the sum, 2 over n, of my errors times xi should be equal to 0. What does that mean? So suppose that your errors, y tilde of I, my error, was equal to k times xi. Suppose that your errors were a linear function of your input xi. If that was the case, then this equation, what that says is that minus 2 over n, the sum of y tilde of I xi, that's equal to minus 2 over n times the sum k of xi squared. So this can never be 0, right? Because x is being squared. So what this tells us is that for this condition to hold, if you fit the data correctly, which means that you found the parameter w1 correctly, then if you look at your errors, it cannot be a linear function of your input. So if you fit your data to a linear function of x, your errors should not be a linear function of x. You should have taken out all the linear components of your data. So this is why I drew this like this. If you now go back and look at your data and you plot your errors as a function of x, so if you plot your errors as a function of x, you should not see, obviously, something like this. If you look at your errors and they're a linear function of x, then you didn't do it right. So you should be mean 0, and your errors should be uncorrelated to the function that you're fitting. So if you're fitting a linear function of x, your residuals should have no linear components left in them. That's the basic idea. Now, what if you, whoa, what happens there? I don't know what that was about. Okay, so what if you look at your errors? I don't know what's going on. Okay, well, it doesn't matter. So what if we look at our errors, and what we see is something like this. Suppose we looked at our errors, we plot our error as a function of x, and we saw something like this. So now you would say, this is okay. You just used the wrong model, right? This tells you that there's a residual left in your data, but it's a nonlinear function of x. So that tells you the kind of function you should have used to fit your data. It's useful to analyze the errors that are remaining from the residuals. All right, so next topic I want to show you is, again, in regression, but now what we have is that I want to solve the problem not by looking at the errors, not looking at the gradient, but I want to solve it using a matrix approach, so we get a complete solution to our linear regression problem. So we have some input. I'm going to represent with the vector, with the observations, but I'm going to represent with the vector y. And so I have, my first data point, my second data point, and I go down to my nth data point. So this is the observations that I have, and my input at any time, x of I, is going to be equal to, I'm going to put a 1. I'm going to assume that I'm going to have some bias, so I'm going to add a 1 there. Then I'm going to have x1 of I, x2 of I. I'm going to have d of these guys, xd of I. This is my feature space. D features plus 1 for a bias. And I'm going to have some weights associated with those. I'm going to have a W0, W1, WD. So my model is that my y hat for data point I, for trial I, is going to be W transpose xi. So here's W, the vector, transpose. So this is a linear model of my input x, but now my x is a vector, my output is a scalar. So I want to now represent this problem in a matrix notation. What this means is that if you take your y hat as your output, as a matrix, as a vector, so like you have here. So I'm going to put this was my y. I'm going to have a y hat here. That's going to be my estimate. That's going to be a matrix x times a vector w, where the matrix x is going to look like this. 1, x1 of 1, x2 of 1, x3 of 1, xd of 1, 1, x1 of 2, x2 of 2, xd of 2, 1, x1 of n, up to xd of n. So that's the matrix that describes my inputs that I have. And so now I can write this equation, that my prediction for the entire data set, y, this vector, is going to be the matrix x times the vector w. And what I want to know is, what is w? How can I find w? You give me x, you give me y, I want to know what's the best w. So the loss function was the difference between what you predicted and what you observed squared, averaged over all your data. So the loss, I'm going to call it j, is, we can write it in matrix notation as 1 over n, that's the number of data points that I had, the vector y minus matrix x times w transpose y minus xw. That's the squared error summed over all the data, averaged over the number of data points. I want to find the w that minimizes this scalar function. So what's important is that the loss is a scalar. It's just a number. So I want to find the w that minimizes this number. All right. So let's multiply this term and let's see what we do. So j, my loss, is equal to 1 over n. I'm just going to multiply these through. The first term is y transpose y. The second term is y transpose xw. The next term is w transpose x transpose y. And the final term is w transpose x transpose xw. X is a matrix, w is a vector, y is a vector. What are the size of these things? They're given up here. So y is a n by 1. W is a d plus 1 by 1. And x is, let me find an x that's not,
on the right.
yeah, let me erase this guy. So what's the size of x? You can see it here. It has the number of columns is equal to the number of data points. So the number of columns is n. The number of rows is d plus 1. These are the size of these elements.
As
Yeah.
average should be from y. of y transpose n plus 1, so n minus 1.
I didn't follow you, Ehsan. Where's the... Oh, sorry. Yes, sorry. Thank you for that. So I don't mean y transpose, I mean y. Yeah. Excellent. So y is an n by 1 vector. W is d plus 1 times 1 vector. So these are column vector, and a matrix X. Okay. So now what I want to do is to minimize this function with respect to the vector W. dj dw. So let's see what this is going to look like. So j is a scalar. I want to find the derivative of a number with respect to a vector, w. So this should be, the result should be a vector that's going to look like this. What's the size of this vector?
D plus 1 by 1.
Yes, d plus 1 by 1. So what are we doing? We have an equation. If you multiply all these guys out, you're going to get some equation that's going to have elements in there that's going to be w's, and elements in there where w is going to be squared, w transpose w. So it's just some big long equation. When we find its derivative with respect to w, what that means is that the first element of this vector is going to be the derivative of this j with respect to w0. The first element of w, this element here. Find the derivative of it with respect to w0. Then we find the derivative with respect to w1, so forth, until we get to the last one, wd. So we end up with a vector that is of the size d plus 1 times 1, which is the size of w. Does that make sense? This is what it means to take a derivative of a scalar with respect to a vector. You just end up with vector size number of equations. And to find the optimum w, the vector w, all of those equations have to be equal to 0. Because that's the derivative of j with respect to w. So this has to be equal to 0 if we found the optimum w. This equation evaluated at w star has to be equal to 0. So our question is, what is this w star? All right, so let me find it for you. All right, so what is the derivative of this equation with respect to w? The derivative of the first term with respect to w is 0. All right. Now, let's look at the second term, this term here. You have y transpose xw, you have w transpose x transpose y. So you see that this is the transpose of this, right? Right? And the other important thing is, this is a scalar. This is just a number. So we can set them equal to each other and add it. So this is the same thing as this, transpose, and we can indeed transpose a scalar and we get the same number. So I can write this term here as minus 2 times y transpose xw. Okay, so now I want to find the derivative of this with respect to w. It's going to have a 2 in the front of it. Let's see what's going to happen. So this equation here, y transpose xw, it's a scalar, obviously, right? Y transpose times w is going to be a scalar. But to find this derivative with respect to w, we're going to end up with something that's going to have a y and an x in it. Now the question is the derivative of this with respect to w, is derivative of y transpose xw with respect to w, is it equal to y transpose x, or is it equal the transpose of this, which is x transpose y? The answer is, look what we have to get. the derivative of j with respect to w has to be a vector, right? And it's going to have to be a column vector. So y transpose x, is that a column vector? No, it's a row vector. The answer is the derivative of y transpose xw with respect to w is this. This is the column vector that we're looking for. Finally, we have this quadratic term in the front. And the derivative of this is going to be either this term in the front of it or this term in the back of it. And basically, the way you can tell what the derivative is going to look like is that which one gives you the correct shape, a column vector. What do you think? Is it going to be w transpose x, or is it going to be x transpose xw? Yeah, it's going to be plus 2 times x transpose xw. So we'll practice this a lot in this class, taking derivatives of scalar quantities with respect to vectors. And the guiding, yeah?
Isn't W transpose X W an identity matrix?
Why?
Because the transpose is...
It's a scalar.
Yeah.
So of course, it's a scalar, it transposes itself.
Okay.
Yeah. So our question was, when we find its derivative with respect to w, is it going to be this term in the front, or is it going to be this term in the back? And it's going to be the term in the back because that's what gives you a column vector. Now, you can always check this by actually taking a vector w and a matrix x and multiply it by each other, and you get a scalar quantity, and then take its derivative with respect to w and check to see this is how it turns out. And indeed it does. All right, so what we have now is that we have dj dw is going to be equal to minus 2x transpose y plus 2x transpose xw. This function is equal to 0 when it is evaluated at w star. So when w star, the optimum w is found, we have found we have minimized the cost, dj dw. So when is this equation equal to 0? Well, we have 2, well, let me get rid of the 2 since we don't need it anymore. So from this we can write x transpose xw is equal to x transpose y, which means that w star is going to be equal to x transpose x minus 1 x transpose y. This is called a normal equation. So if we had the problem as follows, let's summarize what we did. We started out with a bunch of observations. We had features that we represented with vector x. We had unknowns represented with w vector. In order for us to minimize the loss function, the equation that does that is this, x transpose x inverse times x transpose y. And if you look in the literature, what you will find is that this is called the pseudo-inverse. Inverse of x. This part here, up until y, that's called a pseudo-inverse of x. All right, and so the normal equation gives us the solution that we were looking for, the optimum weights for a feature space of x to fit to an observation space of y. Well, we've been using these linear functions where x was, as I showed you, a vector that made up of some linear elements that multiplied by w. What if we have some nonlinear elements? So suppose that we have y is equal to w0 plus w1 of x plus W2 of x squared plus, you know, whatever, some nonlinear functions of x. It doesn't really change our problem because we still can write our problem as follows. So y is y1 to yn. This is all the data that we have. We have the matrix X that we represent as 1, my x1 of 1 plus I have x of 1 squared. Sorry, not plus. The second element is. So I can have nonlinear functions in my observation matrix. So I can have the squared. I can have whatever, log of x if I've wanted on this, so forth. And so I can still write this as a linear function of my w's, like this. It doesn't change my problem. I can still find the solution using this equation that I wrote here, except that x's here are going to have nonlinear elements in them now. They're going to do some nonlinear functions of x. They're going to have Gaussians there if you like. So how do I know that this complexity that I've added is improving my fit? Because you can have linear functions of x, squared functions of x, any power of x you would like. So how would you know that your model is appropriate for your data? And that's the topic of cross-validation. I'll briefly describe this for you. So suppose you have some data points. And if you fit a line to that, it'll look like this. But if you fit a model where you have these nonlinear functions of x, then you're going to fit the data better. It's going to look like this. So this is the wiggly line is when I have nonlinear functions of x that I've added to my problem. Well, how do you know that you didn't overfit the data? The basic idea is that if you have fitted your data to your model and you take one data point out, so instead of fitting it to all the data, take one of them out. Say this data point here. Say take this one and don't fit it to the data. What happens is that your model, when it has many degrees of freedom, it'll do things that will look like this. Without that data point, its behavior will change a lot. So what cross-validation does is that it asks, if you fit the data to everything except one data point, how well does it fit? And if you look at this error in cross-validation as a function of complexity of your model, you might find that cross-validation error declines as the model complexity increases, but then if it becomes too complex, cross-validation error will increase. So there's going to be, if you're lucky, a location in this cross-validation space where you get the minimum cross-validation error. So let me write this down for you in terms of a graph. So suppose on the x-axis I have model order. So say that I have a quadratic model, which would be the order of it is 2. If I have a cubic, its order is 3, or whatever. I can have a 10th order model. On the y-axis, I'm going to plot the mean squared error. So if you take all the data and you fit it to the model, what happens is that your mean squared error declines as the model order increases, right? Typical. You fit the data better as your order of the model increases. But let's plot the cross-validation error. So what is the cross-validation error? So cross-validation is in cross-validation, we fit all the data points except one point. and then we repeat that for all the points. We measure error at the test point. Then we repeat over all points. Then CV error is average error over all the test points. So what I'm going to do is to plot for you CV error as a function of model order. And typically you're going to find something that looks like this. So as the model order increases, your cross-validation order tends to decrease until you find some place where beyond here, now you're overfitting. All right. Any questions? It's a useful things for determining the order of your model. All right. So suppose that we don't have all the data. Suppose that we're going to have to learn and make predictions one data point at a time. And now I want to show you an algorithm that does that. That's called LMS. So, online learning. And I'm going to solve this problem for you graphically. So what we have is that we have some feature space X represented by this vector in some trial N, and we have some vector that represents our weights in that trial. Now I'm going to ask, how should I change W so that it reduces the difference between what I'm predicting and what the data is that I'm observing? So my prediction, right, my prediction on trial N is Wn transpose times X of n, right? That's what I mean by prediction. So what is this Wn transpose X of n? What does this mean? So Wn transpose X of n is the magnitude of vector W times the magnitude of the vector X multiplied by the cosine of the angle between them. So there's some angle between these two vectors, alpha, and this scalar quantity, W transpose X, is the magnitude of W times magnitude of X times cosine of alpha. So this tells us that, well, okay, this quantity cosine of alpha is Wn transpose X of n divided by the magnitude of W times the magnitude of X. Okay, well, what's the projection of the vector W onto X? So if I project this onto X, what do I get? I get some length, P. What is this relationship? So W of n, when I project it onto the vector X, it also depends on this angle alpha, right? In fact, it depends on something that has to do with the cosine of it. So the vector, the length P is equal to the length of the vector W times cosine of alpha. All right, so when I project W onto X, I get a length P, and here it is. is also related to cosine of alpha. So what is this guy here? What is cosine of alpha? It's what I wrote here, which is equal to this Wn transpose x of n divided by this. If I just simplify that, I get my y hat of n divided by x of n. So when I project w onto x, I get something proportional to y hat. Now what I want is something that is proportional to actual y. So the data that I actually want is not y hat, it's y. Let's say this is y. So instead of my projection onto x giving me p, I wish that it had given me this length, that is y divided by x of n. What it gave me is y hat divided by x of n. What I wish I had given me is the vector y divided by x of n. So that means that I should change my w by some vector delta so that now when I project it onto x, I get this quantity, y divided by x of n. So this quantity that I need to change my w by is delta. So I want to change w so that I become something better. So I want to add this delta to it. And if I do it, this delta is chosen well, then I will be able to completely account for the actual data. So what should this delta be? Well, this delta is the difference between this quantity, y divided by x of n, and p, which is my prediction, y hat divided by x of n. So delta is this vector that is y of n divided by x of n. This is what I should have gotten, minus what I did, which is y hat. This was p. This is a scalar quantity, and I want it to be in the direction of x of n. So that's a unit vector that's in the direction of x of n. That's how I should correct my prediction, w, if I want to completely account for the data. So what is this quantity? So this delta is equal to, what's in the numerator? It is y of n minus y hat of n divided by x of n, multiply this through, squared, times x of n. This is if I wanted to completely remove the error, which means that my learning algorithm becomes like this. W of n plus 1 is equal to W of n plus some fraction of this error that I want to remove. I'm going to put an eta in front of it, times 1 over x of n squared times my error, my prediction error, times x of n. This is my learning algorithm. It's called LMS. You take your prediction error, you weigh it by the inverse of the square of the size of the input. You project it onto your input. And that becomes how much you should change your weight. Yeah?
Why do you multiply by n? The coefficient?
Eta?
Or eta? Oh.
Because if you completely remove the error, that would make it so that you are learning 100% of your prediction error, which is okay if you want to do it. There's no harm against it. It just means that you're assigning nothing to noise. typically you don't learn from 100% of the error. Typically you say, I'm going to learn half of it or something like that. The important thing, though, is that you see that error is weighted by the size of the input, x. That's the key idea here. All right. Okay. So we can't prove that this algorithm is going to converge. Because ideally what you want to show is that whatever algorithm that you have in trial-by-trial learning is going to converge to the optimum solution, which was the equation that I showed you, x transpose x minus 1, x times y. If you had all the data, you know what the solution is. That's the normal equation. It's this equation here. So if you had all the data, this is the solution to your problem. Now, if you have only, one data point at a time, then we have an algorithm that tells us how to learn. But we don't know if this algorithm is going to converge onto that optimal solution. If it did, then we'd be happy. We would say that this is going to find the optimal solution. So we have no proof that this algorithm is going to converge onto the optimal solution. However, there is a version of this algorithm for which we can prove that it will converge onto the optimal solution. And that version of the algorithm is called steepest descent. And this is a version of the algorithm that relies on the following assumption. So we're going to assume that my estimate on the next trial is going to be my estimate on the previous trial plus some fraction of the error, where the error is going to be the sum over all the trials. So I'm going to change my nomenclature here a little bit. So let me call these, because I showed you, my data points were called n, so I'm going to call these I. So I'm going to assume that we have all the data and we want to minimize our loss function. And here's my algorithm. So my algorithm says, take all the data points, make your predictions about those data points, take your error at each data point, multiply it by the input. So this is a scalar, this is a vector, sum it all up, multiplied by some number, eta, smaller than 1, and update your weight. So this is updating the weight based on the average error that you get from a particular W. So now the question is, all right, can I show that this algorithm is going to converge? So if I write the sum in matrix notation, I have something that looks like this. Where, as before, my W is a vector that looks like this, and my X is a matrix that looks like this. So that's my inputs that give me the matrix X. My W is a vector. This is my learning algorithm. It says that my W on the next iteration is my W in the previous iteration plus some average error that's been multiplied by my input X. And what I want to know is that if this is, yeah?
Do we have bias term here? W0 and 1s in the X?
Let's just assume that, that's x1 is 1, let's say. So I didn't have an explicit bias here. We can add that to it. That would start with the W0. All right, so I want to see where does this algorithm converge to? This is my interest here. So let's begin with the first iteration. So W1, I'm going to start with some random weights, W0, and then what I'm going to do is add to it the difference between what I observed and what I predicted. So this is what this algorithm says you should do. And so we can write this as follows, which is equal to, let's sum up, let's collect these W0s. I get this identity matrix minus eta x transpose, there's this W0 here, times W0 minus eta, I guess plus x transpose y. All right, what's W2? That's equal to W1 plus eta x transpose y minus x W1 which is equal to sorry, identity minus eta x transpose x times W1, where W1 now is this. Which is equal to okay, similarly I can write W3. It's going to be equal to, if I multiply it out, I minus eta x transpose x cubed times the initial condition W0 plus I minus eta x transpose x squared eta x transpose y plus I minus eta x transpose x eta x transpose y plus eta x transpose y. In general, I can write that W at the end, infinity, is going to be equal to, oh, let me put down, instead of infinity, let me put down long time in the future. So W at the iteration, let's call it, that's okay. I mean, we're going to keep on iterating. I guess we're interested in convergence, so I'm going to put infinity as the last time point of my convergence. That's going to be equal to, I want to write it as a sum. All right, I keep going back and forth. All right. So I'm just going to write this W3 as a sum now. At the third point, it's going to be equal to I minus eta x transpose x cubed W0 plus the sum of I is equal to 1, 2, 3 of I minus eta x transpose x raised to the power of I minus 1 times x times eta x transpose y. So I just wrote this equation now as a sum. Let's see if I did it right. Yeah, I think it looks okay. So then my W at the end is going to be equal to I minus eta x transpose x raised to the infinity times W0 plus the sum of I is equal to 1 to infinity of I minus eta x transpose x raised to the power of I minus 1 times eta x transpose y. So what I'm interested in is that what is this quantity here? Does this have anything to do with what we had in the previous set of results, which said that W should be equal to x transpose x minus 1 x transpose y. So what is the relationship between these two equations? Does this converge to this? And I want to show you that it does. And so we'll learn a little bit of math to see how to do that. So what do we have here? We have a sum of some quantity raised to a power. And let's see what happens to these kinds of series. So suppose instead of this fancy matrices here, suppose we just had a scalar. Suppose here's was our problem. We had this geometric series that looked like this. Some number a raised to the power of I minus 1. So suppose I want to find this sum. What is this? This is a raised to the 0 plus a raised to the 1 plus a raised to squared plus a raised to the n minus 1. Right, so let's call that some number s of n. I want to know, what is this s of n? What is this number here? To find this s of n, here's what we can do. So of course a here has to be less than 1, right? Otherwise it's not going to converge. A has to be less than 1. Look at this equation here. This term here, it's going to be a vector, right? This quantity here is going to be something, in this case it's going to be a matrix. So for it to be raised to a power and not explode, its eigenvalues have to be less than 1. For it to scalar to be raised to a power and not explode, its value has to be less than 1. So let's do it for the scalar first. So we have some scalar a raised to some power, and we're going to sum it up. Here it is, I summed it up here. Now I want to know what this sum is. So how do I find that? Well, let's multiply this quantity here by the number a. Now what is this? That's a times s of n, right? That's equal to a plus a squared. It's a to the n. So now, if I take s of n minus a times s of n, what do I get? I get 1 minus a to the n. So what this means is that s of n is equal to 1 minus a to the n divided by 1 minus a. This is what the sum converges to. So we have a geometric series. Geometric because the quantities in the series are raised to a power. When we sum it up, it converges to a quantity that's a ratio that looks like this. So the sum of I is equal to 1 to n of a to the I minus 1 is equal to 1 minus a to the n divided by 1 minus a. So as I don't know what happened. Holy cow. Okay, here it is.
It's good.
All right, it's over here. Okay. Phew. Okay. So as n goes to infinity, the sum of I is equal to 1 to n of a raised to the power I minus 1. What happens to that? That's equal to 1 over 1 minus a, given that the magnitude of a is less than 1. So the sum converges. As n goes to infinity, this quantity becomes 1 over 1 minus a. Yeah, you see that? Sum of a geometric series where the quantity, some a raised to a power, that sum converges to 1 over 1 minus a. All right, so if you have a matrix of I is equal to 1 to infinity of some matrix A raised to the power of I minus 1, that's going to be equal to the identity matrix minus A, the inverse of that, if all eigenvalues of A are less than 1. Okay, so let's go back now to our problem. We had this thing. We said W at the end of it, at the end of our algorithm, is equal to I is equal to 1 to infinity of identity minus eta x transpose x raised to the power of I minus 1 eta x transpose y plus I minus eta x transpose x raised to the power of infinity times my initial condition W0. So this term here is going to be 0 if all values of I minus eta x transpose x are less than 1. So if that's true, then what I get is this sum of this term raised to the power of I minus 1. Well, the matrix raised to the power of I minus 1, the sum of it is the identity matrix minus that, its inverse. So this is equal to the sum. This sum is going to go away. I'm going to have now the identity matrix minus this term, I plus eta x transpose x minus 1 times eta x transpose y, which is equal to eta x transpose x minus 1 times eta x transpose y. So then W at the end is x transpose x minus 1 x transpose y. That's what was our normal equation. So the steepest descent algorithm converges to the normal equation. Okay, so what did we learn today? We learned LMS. We learned how to change our estimate from trial to trial. The way we do it is that we look at our error, we project it onto our input space x, we divide it by the magnitude of the input x. That's how much we should change our weight. We learned about cross-validation, how to check the power of our algorithm. Basically, the more complicated your model is, the better you fit the data, but you run the risk of overfitting. So by using cross-validation, you can check to see are you overfitting your data. We learned about convergence of geometric series and why that's useful in evaluating the steepest descent algorithm. Okay. Good luck with the homework. I'll see you in a couple days.
Same.